Awesome. So, what do y'all remember about slope?
Y equals mx plus b.
Yeah. So, it's the equation of a line, right? Y equals mx plus b. And the slope of that line is written as n. What does it tell us, though? Like, what is slope?
The rate of change.
Yeah, no, that's exactly what it is. Absolutely. It's the rate of change of that line. It's how steep that line is, right? It tells us for every 1 unit over x you move, you go so many units in y, right? It's that relationship between the two. And that's what we're going to be talking about for the most part today, as well as a little bit into functions. So, first thing to note, if a slope is positive, the right side of your line is going to be hiked up higher than the left side. Conversely, if it's negative, it's going to be the opposite case, right? Where the right side is lower. So just by looking at a line, we already know something about it. We already know if its slope is positive or negative. We know something about that m value. Everybody with me on that? Moreover, if we can see what the intercept is, and we can see how this is kind of hashed out, then automatically we know the equation of it without actually knowing the equation of it, right? Make sense what I mean? Yep. So, the equation of a line is mx plus b, everybody's second least favorite equation, followed by the quadratic formula, right? Like how many times are we going to talk about either one of those? Anyhow, so this equation, mx plus b, is the equation of a line. All it tells you is that if you get some x value, you're going to multiply it by that slope, right? Because that tells you how much you're going to move up relative to each unit over. And then when x is equal to 0, what's y going to be? What's that y-intercept? Make sense what I mean? Yeah. Having said that, there is one particular case that this doesn't exactly cover. The vertical line. The vertical line is the case where x is equal to some constant. And in that case, you don't have a slope. It's undefined. Now let's think about this for a second. If we took a line with positive slope, and we kept tilting it up and up and up and up and up, eventually it would be a vertical line, right? So if we think of it this way, we can kind of see how this would be undefined, right? Because eventually that slope approaches something like infinity. Agreed? Yeah? And that's why the vertical line, in an intuitive sense, why it's undefined, why it has undefined slope. Everybody with me on this? Yep. So, having said that, let's imagine we're given A. We wanted to graph it just really quickly, right? First thing we might want to do is jump right to that y-intercept. That's going to be an easy thing to find, right? From there, we can say, all right, if I know the slope, which in this case is 2, I'm going to go over 1 unit, and then I'm going to go up 2 units. Then I'm going to go over 1 unit and up 2 units. So what does this look like? Something like this. I'm going to say this is that 0, 1, right? Now we're going to go 1 unit over, up 2 units. Dope. Go ahead and mark that. Just for good measure, let's do that one more time. And now we're somewhere where I can't draw. And put a line through those points that we just plotted. This is one quick way of going about it. Having said that, in the case that y is equal to 2, what is that?
The slope isn't defined, so it's undefined.
Not quite. In this case, the slope is defined. Because it's not x equal to 2, right? It's y equal to 2. In this case, it's like saying you have 0 times x plus 2. Make sense what I mean? So what would that look like then?
Horizontal line.
Exactly. It would be the horizontal line. That's exactly what it would be. And why is that? Because, well, 0 is between all of your positive numbers, all of your negative numbers. And if we think back to this situation, right? In order for this to move to a negative direction, we have to pull down this end, right? Similarly, we would have to push up on this end. Well, at some point, we're going to pass through slope that's equal to 0. And that one point would be when they're horizontal. We can think of it in a sort of intuitive way like this. Having said that, looking at this example that I just drew on the board, notice they did the exact same thing, right? They go to that initial point, jump over 1 unit, jump up 2 units. And then at that second example, same idea. Like it was just saying, here, we're saying m is equal to 0. Because m is equal to 0 is just the horizontal line. Is everybody with me on this? Yeah? Dope. Having said that, I'm going to run through these really quickly. These are just examples that I wanted to leave in case y'all wanted to look over some examples at home. Having said that, let's skip to here, to this, the slope of line passing through 2 points. So we've got 2 points that we know sit on the line. We want to know what the slope of that line is. Well, it's going to be the difference in our y values divided by the difference in our x values, right? It's going to be delta y over delta x. That's all it is. And again, remember, this delta symbol just means the difference. How much did you change moving in that forward direction, right? Like, we know where we start. That's our 1 spot. We know where we end up. That's our 2 spot. What's the difference between those? That's all this delta means. Having said that, so we see here that we can get, like I said, the slope of this line. Notice though, it doesn't really matter when we calculate slope and all. It doesn't really matter the order that we take our difference in, right? Like y1 minus y2 versus y2 minus y1. It doesn't matter so long as your denominator and your numerator agree in that direction. Does that make sense what I mean? Yeah? And that sort of ordering. As long as that's preserved between your denominator and your numerator, you're good. And this kind of makes some sense, right? Because that ordering, it tells you something about the direction you went. So if you go in one direction in your denominator, in the opposite direction in your numerator, gestured backwards. If you do that, then you're going to naturally end up with a negative sign that shouldn't be there. Does that make sense what I mean? Yep. Dope. So, really quickly, why don't we all try to find the line, the equation for the line in C? See if y'all can find that really quick. For those of y'all at home, can you see the projector well? Awesome. All right. So, you said -5, correct? Yeah? What about the equation for the rest of the line? So this is just the slope, right? -5.
Y equals -5x plus 4.
Y equals to -5x plus 4. So let's see. Well, we don't really need to see, right? Because we know the slope. We found the slope, right? And then we know what this this intercept point is that was given to us. We know 0, 4 was an intercept. So just from those 2 points of information alone, we know that m is -5 times x plus 4. Automatically, just 2 points of data gives us the entire equation for the line. Does this make sense to everybody what I mean? Yep. Awesome. Those of y'all at home, how can you hear me over here? Can y'all hear me? Awesome, cool. All right, so this brings up the point that I wanted to make next about point-slope form of the equation of a line. What it tells us is that knowing just the slope and a single point on our line is enough to give us the entire equation of our line. So before, in that example, we took advantage of the fact that we had the intercept, right? Like knowing that gives us our b. That's pretty convenient. However, any point will do. Just knowing, like I said, the slope and 1 point, you're done. You know everything you need to actually derive the equation for this line. So as an example of that, we've got this line with slope 3, and it goes through the point 1, -2. Using point slope, what we've got is y1, or y minus y1 is equal to m times x minus x1. Plugging in everything, y minus -2 is equal to 3 times x minus 1 is equal to y plus 2, 3x minus 3. We're going to subtract 2 from both sides. And when we do, we're going to find that this is equal to, or this gives, y is equal to 3x minus 5. It's actually kind of a quick process, right? Like, all we just did is basic algebra. Nothing major yet. I'm checking our work. Turns out to be the same thing. Notice again, this illustrates a point that I've made a couple of times. It's 1 unit in the x to every m value, right? So whatever your m is, it's the relationship of how far up you go or down relative to 1 unit across. Cool? All right, so that, let's get through. Now, there are a couple of different equations of lines that I want y'all to know, to kind of commit to memory. And they are as follows: the general form, the vertical line, the horizontal line, slope-intercept form, and the point-slope form. These are, like I said, all in your notes. These are all in your notes. You can find them in week 1 under slide 98. Very cool. So chugging along. There are, however, 2 things that you should know about parallel lines and perpendicular lines. Let's say I give you this, and I want you to find a line that's parallel to it. Knowing that two lines are said to be parallel if their slopes are equivalent, that tells you automatically you can come over here and say, we just need to change our b, right? Just need to move it up and down. We're not going to change the way it's slanted, Because if we did that, then it wouldn't be parallel anymore. So, giving you the equation of one line and asking for another parallel line automatically tells you that the only thing you need to change is your B. Make sense? Similarly, if you want it to be perpendicular or at a right angle, you would just want to take this slope and change it, right? So let's imagine on an exam I said, here's a line. I'm going to rewrite this. Y is equal to 3x minus 5. Here's a line. Give me another one that's perpendicular to it. All you need to do, find the slope. It's given to you, right? And replace it with its negative reciprocal. What that means, so this is y1, y2, be negative 1 over 3x minus 5, or minus whatever. Is everybody cool with this? No?
Wait, I actually have a question. So,
Yes, sir.
on the, like a perpendicular line, how would you find like where the y-intercept would be? Because like, would it be in the same?
Well, this is a good question, right? Like, how does this work? Let's look at it. Let's think about it for a second. Let me actually go. Back. Yeah. All right. Let's imagine we had a line perpendicular to this, right? If we move it up and down, just up and down, all of those other lines will stay perpendicular, right? And they don't change in that way. So our B doesn't matter here as much as our M does. Does that make sense? Does that answer your question?
Yeah, I think so.
So to draw it out, let's say we've got this slope here, or this line here. And it looks to be something like, I don't know, negative 1x plus 1. Now let's say we want the line perpendicular to it. So we find a line that's perpendicular to it. Line 2 is so we find a line that's perpendicular to it. This one goes straight through the origin. Now let's say I wanted to move this line up 2 units. So we're just going to add 2 to it. Well, line 3 is still perpendicular to line 1, right? But it's parallel to line 2. What this illustrates is that as long as the slope is the negative reciprocal, then the lines are going to be perpendicular. As long as the slopes are identical, the lines are going to be parallel. Is everybody with this? Yep. Does that answer your question?
Yeah, I have another question, but I'll ask you after class because it was about the homework specifically.
Gotcha. For the record, for those of y'all who didn't see, I did not remember to give you the extension, did I?
No, it says it's due tonight.
Oh, is it?
Yeah.
I was planning on pushing it back to Friday.
Oh.
Initially, it was marked as Sunday by accident. I meant to hit Tuesday and just like, I'll come back to it later, and totally forgot to come back to it. It happens. But yeah, I intended to give it to y'all until Friday. Having said that, and carrying on, this illustrates the same idea as what I was just trying to make, or the same point. We've got two lines that are clearly parallel to each other. Their slopes are the same. Then we've got this one other line that's perpendicular to those two parallel lines. The only thing that's different, really, in a meaningful way, is that the slopes between these two and this, they're just the negative reciprocals. Yeah? Having said that, that was the end. Let's jump into functions. All right. Who knows what the definition of a function is other than what's up here? Like, can you tell me generically what a function is? Let me ask it a different question, or in a different way. Holy shit, that was crooked. I'll bleep that out. All right. So, let's say we're given a function or an equation, and its graph looks like this. Let's say we're given another one, and its graph looks like this. Which one of these is a function?
The one on the right.
The one on the right? Who agrees? Few hands? Yeah.
Excuse me.
This one is a function, this one is not. And the reason why is because what a function does, what it is an equation that takes in one x value and gives you one y value. So for every x input, you should only get one y output. This clearly doesn't do that, right? Well, let's say this is the point 1, or x equal to 1. Well, if that's the case, then this equation obviously has two different y values for that x, right? Make sense what I mean? So one way to think about what a function is graphically like this. I personally prefer thinking of it like this because I think it's a bit easier to understand. Having said that, there's some details we need to know. In particular, we need to know what the things are called that we put into it, what the things are called that we get out of it. All of the x's that we put into our function, they come from what's called the domain. All of the y's, they belong to what's called the range. A way to visualize this, there's two different ways. One way we can think of the relationship between the domain, the range, and our function is this. What we've got up here is a collection of numbers represented as our big or outer circle. And this funny R represents real numbers. So we're just pulling numbers out. That's what this bigger, like I said, circle is. And inside of it, there's a particular set of those numbers which we can feed to our function. Those are our domain, or that is our domain. Does that make sense, what I mean? Kind of, sort of? You can think of it like you're an allergic, and Grandma has this big bag of stuff that you can eat from, but you have to pick out what you can and can't eat, right? Like you can't eat the Snicker bars because they have peanuts in it, and you're allergic to peanuts like I am. But you can eat the Skittles. That's kind of what this is saying. You've got this collection of values, and you can only put a handful of them into your function. And that handful could potentially give you any number back, but it only gives you a particular set of those numbers. Does this make sense what I mean? Yeah? Another way to visualize this is like this. Let's imagine if you shine a light onto this graph, down onto the x-axis, right? So our light is perpendicular to the x-axis. Wherever there's a shadow representing our graph, that would be the range. Similarly, if we do it to the y-axis, shining a light perpendicular, wherever there's a shadow, that would be, sorry I said that backwards, the domain, then the range. Does that make sense what I mean? Yeah? Everybody with me on this?
Is the shadow going from the line to the x-axis?
Yeah, sort of, right? This isn't a complete, like, perfect comparison, because we could have an example like this, right? And then we'd have to have two lights. But it's in general this idea of, if we were to project somehow our equation back onto the x-axis, like a shadow. The shadow along the x-axis would represent our domain. The shadow along the y-axis would represent our range. Is everybody with me on this? I need more than a blank stare. Is everybody with me on this? Man, I can make y'all get up and do jumping jacks if I have to. Like, is everybody with me?
Yes.
Yes. All right. Awesome. Cool. So, having said that, another way we can think of functions is kind of as machines that take in values from our domain and spit out values that belong in our range. So of these, which of these is a function, which one's not?
A and C are functions.
Yeah, absolutely. A and C are functions. This, we can see this circle, there's a bunch of different x values that have multiple y values, right? Similarly, D, same case. Having said that, how would we find the domain and range of a function? What might we do here? Well, the first thing that would be nice to know is where this square root can take on x values, right? A square root can only take on x values that are 0 or greater. Agreed? Otherwise, we get out an imaginary number. Okay. Well, knowing that, when is x minus 1 going to be 0 or greater? Whenever x is greater than 1, right? So whenever x is 1 or greater, that's our domain. Now, what's our range going to be? What possible values can we get out of a square root? Anybody?
Positive numbers.
Yeah, any number 0 or greater again, right? So in this case, our graph looks something like this. So having said that, the domain here would be x greater than or equal to 1, which we could also write in interval notation as x in the interval from 1 to infinity. And the range would be the same, except with 0, right? Everybody with me on that? So we can write this in a couple different ways. So is this making sense to everyone so far? Yeah? How about you all at home? Following along so far? Yeah? Awesome. All right. So, jumping ahead, we get at the same idea, right? The range can be thought of as y greater than or equal to 0, or as an interval. Similarly, the range. And to find that, all we did was take a couple facts, right? Like, we know what values the square root can take on. We know what we can put into it, and we know what we can get out of it. So, just by knowing those two things, we can figure out what the domain and range of it is. So let's say I asked you instead to give me what the domain and range is of, let me write it on the board. Give me the domain and range of this equation. What would that domain and range be? How would you find it first? Let's start with the domain. What values can 1 over x take on? Any value that's not 0, right? So, the domain requires us to answer the question, when is x squared minus 4 not equal to 0? Does anybody know that answer? Or negative 2. So the answer to this tells us that the domain is going to be negative infinity, negative 2, unioned with negative 2 to 2, unioned with 2 to infinity. So what this U means is take this interval, add this interval, add this interval. And what the rounded brackets mean is you go up to that value, but you don't include it. So we're going up to negative 2, but we're not including it. We're going up to 2, but not including it. We can be 1.999. It could be 1.9999999. We could be Chuck Norris and say 0.9 forever, but we can never reach 2 or negative 2. So really, this is like saying every number except for 2 and negative 2. Does that make sense what I mean? Yeah. So having said this, what about the range? What can the range of this be? What do you all think? The range of this, I'm just going to go ahead and tell y'all, is negative 4, my mistake, negative 1 over 4 to infinity. Now why is that? Well, let's look at it in a slightly different way. Let's start by saying what's the smallest number this can give us? The smallest possible number that can give us is negative 4, right? Because if x is 0, then we get negative 4. And if x is any other number other than 0, we get something slightly larger, right? Okay, so negative 4 is the smallest. What's the largest? Really anything, right? Anything close to 0, anything that makes this close to 0. It's going to give us a really big number, right? Make sense what I mean? So in that way, we're going to get up to infinity, but we will never drop below negative 4. Negative 1 4. Right? Everybody cool with this? Yeah? Cool. Having said that, now there's some notation we should know about all of this. Whenever we represent a function as, say, f or g or whatever, all we're effectively doing here is giving it a name. F of x is just the name of our function. It tells us the function f being done onto this value x. So if we know what our function is, f of x is equal to this set of instructions, then when I tell you f of negative 1, you know you're doing that set of instructions onto the value negative 1. Everybody with that? Similarly 0 or whatever. Whatever value we want to put into it. I could also say represent it with G, represent it with H, K, L, M, N, O, P. These are all just names that you decide to give to your function. Is everybody cool with that? Yeah. All right. Why don't y'all try to work on A for a second? I'm going to do B. Not have enough space up here. I cheated. Knew the answer in advance. So who thinks they got A figured out, worked out? Anybody? It's gonna take some time, right? Like this is a pain, I do admit. So having said that, I'm gonna skip straight to it. To work out A, what we would do is every time we saw an X in our original function, right? We would replace that with X plus delta X. Just like what they've done here. Then, go ahead and expand it out. And what you get is this final equation. Similarly, plugging in x plus delta x into that first function, subtracting our second function, and then dividing all of it by delta x again, we're going to get to this point. Now, I knew what this final value was going to be because, like I said, I cheated. I took what's called a derivative, and we'll get to that point in this class. But in the meantime, I want to point something out about this. Notice, we're talking about delta x, right? Well, if our function is equal to y, and we move delta x over, right? Our function now becomes associated with a new y value, agreed? So this is y1, this is y2, right? So this is delta y over delta x. Everybody with me on this? Yeah? So this represents the slope of what's called a secant line. And we'll talk more about this thing in future classes, but I just wanted to point out this one important detail, that what this is delta y over delta x. For now, though, let's talk about the composite of functions. All the composite of a function is to say I got function 1, I got function 2. I'm going to do function 1, then I'm going to put it into function 2. Or I'm going to do function 2, and then I'm going to put it in function 1. So, effectively, we're doing our operation, our first operation on our initial input. Then we're taking that output, we're putting it into the other function. Does this make sense what I mean? As an example of what this might look like, we've got two different functions up here, 2x minus 3 and x squared plus 1. The first case, we're going to put g into f. And in the second case, we're going to put f into g. So what we're saying here is do g on x, and then put it into f. What that's going to look like is saying, all right, I know I have f. Every time I see x in my function of f, I'm going to replace it with g. And then, after I do that, I'm going to replace g with its actual instructions. Is everybody cool with this? Then I'm going to reduce it down as much as I can and simplify it because, frankly, that looks terrifying. So let's go ahead and simplify it. This is f of g of x. Similarly, going in the opposite direction. Now, the reason why I write it out, or I put this slide in here with everything together, because I wanted to make a point. I wanted to make a point to say, notice f of g of x and g of f of x, they don't give us the same solution. They're not equal. That's because, generally speaking, f of g of x won't be equal to g of f of x. So the order here matters, right? Is everybody cool with this? Yeah? Cool? All right, so we've got a function, but we now want to go back from our y to our x. We want the inverse function. The inverse function is effectively just a set of rules that says, now that you're at y, how do you get back to x? Right? So, let's say you tell somebody how to get from a little sibling. We tell a younger sibling how to get from mom and dad's house to the mall. Well, given that you just told them how to get to the mall, they should be able to get back, right? This is the inverse function. The process of getting back from the mall to your parents' house would be effectively the inverse function. Having said that, it's a function. So it also needs to be one-to-one. Agreed? Yeah? Another way of thinking about it is, if g is the inverse function of f, and I take and I put x into f, and then I take and I put f into g, I should get back out x. Because g just undoes x, or I mean f, right? Yeah? And vice versa. In this case, if g is the inverse function of f, then that also means that f is the inverse function of g. So the opposite order works here. Is everybody cool with that? Yeah? Having said that, an important observation, an important note to make, something we should all know, is that notice that what f of x does is it says, give me any x value, let's call it a. I can give you a y value back, let's call it b. Well, if that's the case, then the inverse says, give me any b value, I can give you that a value back, right? So the graph of your inverse function is the reflection of your original function across the line x is equal to y. Because you're just swapping those order pairs, right? In the case of f of x is equal to y, you're saying, I've got an x, call it a, right? I'll give you that b back. In its inverse case, you're saying, I've got an x, call it b, I'll give you a back. So we just flipped the orders of a and b in all the order pairs. And this effectively just has the effect of reflecting our graph. Now, some of y'all might have already caught on that if this is the case, then we're gonna have a couple failed cases. We'll talk about that in just a second. But for now, this is another good way of understanding the relationship between our function and our inverse function. Having said that, how are we going to do it? How are we going to find our inverse functions? This is all well and good. I'm giving you a bunch of functions here, and I've told you what their inverse functions are. But I've effectively done nothing to tell you how to find it. What do y'all think? How would we find the inverse function? What would be the process?
Can you flip X and Y?
Yeah, this is part of it. This is definitely going to be the start. So the first thing we say is f of x is equal to whatever our instructions are. Just because I'm going to give this as an example, let's go ahead and say x plus 3. Step 1, replace f of x with y. Step 2, swap x and y. This is that stuff you were just talking about. Step 3, now we're going to solve for y. And finally, step 4, replace y with the inverse sign. Now, looking at this, it's not as obvious as it is with the graph case. There are going to be failed cases. That's where I'm about to head to next. Can anybody guess where one of the failed cases might be? Like what your original function might be that would fail? There's always everybody's favorite x squared. Think about what happens if you take the graph of x squared and you reflect it across x equals y. You get like this sideways looking view, right? So that's got to fail. What do we do when that happens? You're going to do what's called take a restriction. What's called take a restriction? We're going to restrict part of our problem. But before I get there, let's actually see why this fails. So using one of these failed cases, we've got f of x is equal to x squared minus 1. First thing we're going to do, swap out f of x with y. Now we're gonna swap y and x. Now, this is step 3. First thing we're gonna do, add 1 to both sides. Next thing, is we're gonna take the square root of both sides, right? But we can't just take the square root, we've gotta say plus or minus the square root, right? Because we're trying to solve for y. And y can be positive or negative, right? So, plus or minus the square root of x plus 1 is equal to y. This is where we fail. Because look at what happens. We put in 2 different x values, one different x value, and we get out 2 different y values, right? We get a positive case and a negative case. Let's say x was equal to 1, then we would get out a positive square root of 2 or a negative square root of 2. So what we do here is we say, we're just going to choose the positive values, the principal values. Make sense? And in doing that, we say, all right, dope f inverse of x is equal to the square root of x plus 1. And the reason why is because this is the only way to make this equation 1-to-1, to make this inverse 1-to-1. And what we've effectively done is restricted our range, right? We said, yeah, we could get our range from negative infinity up to infinity, but that wouldn't be, in our particular case, 1-to-1. So let's cut off half of it. Let's only consider the part from 0 up to infinity. Does that make sense what I mean? So in doing this, we've restricted our domain, our range, and we found the inverse function. And they're pointing out the same thing. It's not entirely true. This is why I wanted to make this point and why I kind of kept alluding to it over and over again. This isn't entirely true that f has no inverse function. It does. But its inverse function has to be a restriction. Does that make sense what I mean? Like we have to do something to it to make it work. In this case, we're just restricting the range. Having said that, looking at the original graph, we can see why that happens, right? Take that reflection across the line, x equal to y, and what we end up with is this somewhere up here, and then everything else sideways. Yeah. So it has all of these valid points. Having said that, what time is it?
6:43.
I will let you all out. Since we only have 7 minutes and an entire another section coming up. I will stick around if anybody has any questions.
For the homework assignment,